Somewhere out there in the vast darkness of space, a cataclysmic symphony is playing, a sound so powerful it ripples through the very fabric of reality itself. Picture two city-sized spheres of pure neutron matter, each more massive than our Sun but crushed down to the size of Manhattan, locked in a death spiral. When they finally collide, the explosion unleashes more energy in a single second than our Sun will produce in its entire 10 billion-year lifetime. This is the violent, beautiful chaos of a neutron-star merger, one of the most extreme events the universe has to offer. And yet, for all their destructive power, these collisions are also cosmic riddles, leaving behind clues that scientists are still desperate to decipher. What happens when matter is squeezed so tightly that a single teaspoon of it would weigh 1 billion tons? What bizarre forces are at play when gravitational waves shake spacetime like a drumhead, and jets of plasma are shot into the void at nearly the speed of light? Over the past few decades, we've caught glimpses of these mergers through telescopes and gravitational wave detectors, but each discovery only deepens the mystery. From unexplained bursts of gamma rays to strange electromagnetic afterglows that defy physics as we know it, neutron-star collisions are rewriting the rulebook of the cosmos. And that's exactly what we're diving into today. In this video, we're unraveling 25 of the most baffling, awe-inspiring, and downright weird features of neutron-star mergers phenomena that challenge everything we thought we knew about the universe. Some of these mysteries might hold the key to understanding where gold, platinum, and other heavy elements come from. Others could reveal hidden laws of physics lurking in the most extreme environments imaginable. By the time we're done, you'll see these cosmic collisions in a whole new light, not just as explosions in the void, but as cosmic laboratories pushing the boundaries of what's possible. So buckle up, we're about to journey into the heart of one of the universe's greatest enigmas. One of the strangest cosmic contradictions lies in the aftermath of neutron-star mergers, where the universe should be overflowing with gold but somehow isn't. For decades, scientists believed these collisions were the ultimate cosmic forges, responsible for creating most of the heavy elements in the universe, from the platinum in jewelry to the uranium in nuclear reactors. The math seemed flawless. When two neutron stars collide, the explosion spews out neutron-rich material at incredible speeds, creating the perfect conditions for rapid neutron capture, or the R process, which builds heavy atoms like gold. Yet when astronomers tally up the actual gold in the cosmos, something doesn't add up. Recent observations of merger remnants reveal far less gold than our models predicted. In 2017, the landmark collision detected by LIGO and Virgo, dubbed GW170817, should have produced mountains of heavy elements. But follow-up studies found only a fraction of the expected gold. The same mismatch keeps cropping up in other mergers, leaving astrophysicists scratching their heads. Could our understanding of the R process be flawed? Are these explosions ejecting material in ways we don't yet grasp? Or is there a hidden channel, some other cosmic phenomenon, contributing more gold than we realize? Theories are flying. Some suggest that the gold might be locked inside dense, fast-moving jets that telescopes can't easily detect. Others argue that mergers in the early universe operated differently, producing far more heavy elements than their modern counterparts. Then there's the wild card. What if black hole mergers, not neutron stars, are secretly doing some of the heavy lifting? Until we solve this, the glittering mystery of the missing gold remains one of the most compelling puzzles in astrophysics, proof that even the universe's most violent events still keep secrets. But perhaps even more baffling than missing gold is the way neutron star mergers fire material into space. When these cosmic powerhouses collide, they don't just explode. They launch jets of plasma at nearly the speed of light, so energetic they can outshine entire galaxies for a few blinding seconds. These jets should be sleek, symmetrical, and razor-focused, like cosmic blowtorches slicing through the void. Yet time and again, observations reveal something far messier. Instead of clean, twin beams, we often see lopsided structures, one jet dominating while the other flickers weakly or even appears missing entirely. Some mergers spit out fragmented sprays as if the jets are collapsing mid-flight. In 2020, astronomers studying the aftermath of a merger 390 million light-years away found a jet so off-center it looked like a fire hose flailing in zero gravity. This isn't just a visual oddity, it's a direct challenge to Einstein's theory of relativity, which predicts these jets should form with near-perfect symmetry under such extreme conditions. The implications ripple through astrophysics. These distorted jets could explain why some gamma ray bursts the universe's most powerful explosions very wildly in brightness. If the jets are unstable or uneven, their energy might not reach us in a clean, predictable pattern. Some researchers now suspect magnetic fields, stronger than anything we've modeled, are twisting the jets like cosmic corkscrews. Others argue the debris left behind by the merger forms an invisible obstacle course, scattering the jets before they escape. Every lopsided outburst forces us to rethink how matter behaves when pushed beyond all known limits, proving that even in death, neutron stars refuse to follow the rules. When two neutron stars collide, they don't just merge, they ignite. The resulting explosion, called a kilonova, should theoretically follow a predictable script, a burst of light that peaks within days before fading into the darkness of space. But the universe loves breaking its own rules. Some kilonovae shine 10 times brighter than our models predict, while others flicker out mysteriously fast, barely registering on our telescopes. This glaring inconsistency, the kilonova brightness paradox, has astrophysicists questioning whether we've misunderstood these cosmic fireballs entirely. Take one of the brightest kilonovae ever observed, detected in 2020. Blazing with the intensity of 1,000 supernovae, it defied every simulation by staying luminous for weeks. Normally, kilonovae fade as their radioactive material decays, but this one seemed to have an unseen power source, almost like a hidden engine stoking the flames. Then there's the opposite extreme, mergers like the one spotted in 2018, which produced a shockingly faint afterglow. Instead of the expected fireworks, it dimmed so quickly that astronomers nearly missed it altogether. So what's behind these wild variations? One leading theory points to the composition of the material ejected during the merger. Neutron star debris isn't just uniform sludge, it's a chaotic mix of ultra-dense matter, some packed with heavy elements like lanthanides, which absorb light and mask the explosion's true brightness. If a merger churns out an unusual amount of these elements, it could explain why some kilonovae appear dimmer than they should, but that doesn't account for the absurdly bright outliers. That's where stranger ideas come into play. Some researchers suggest magnetic fields, intensified to ludicrous strengths during the collision, might be converting rotational energy into extra light, essentially turning the merger remnant into a temporary powerhouse. Others speculate that certain kilonovae might ignite short-lived black holes, whose feeding frenzies pump additional energy into the surrounding debris. And then there's the curveball. What if some mergers produce exotic states of matter like quark-gluon plasma, releasing energy in ways we haven't even begun to model? The kilonova brightness paradox isn't just a technical hiccup, it's a glaring gap in our understanding of how matter behaves under the most extreme conditions imaginable. Every outlier forces us to rewrite the physics playbook, reminding us that even the universe's most spectacular explosions still hold back their deepest secrets. Some neutron star mergers keep talking long after the initial explosion, and we're still struggling to decipher what they're saying. Imagine witnessing a colossal cosmic collision, watching the brilliant flash fade only for a mysterious radio signal to flare up weeks or even months later. These delayed emissions make no sense under our current models. When neutron stars merge, the explosion should send out a burst of radio waves almost immediately, produced by the shock waves plowing through surrounding gas. But what we're seeing defies expectations, eerie afterglows that ignite like clockwork, long after the fireworks should have ended. Take the merger event GW170817. For days, telescopes saw nothing unusual in radio wavelengths. Then, over 160 days later, boom, a radio flare blazed to life, brightening for months before vanishing. Similar delays keep cropping up in other mergers, with some flares appearing as late as 300 days post-collision. This isn't just a minor inconsistency, it's a glaring hole in our understanding of how these events unfold. If the debris from the merger is moving at near light speeds, how can it still be interacting with its surroundings so long afterward? One possibility is that we're seeing the fallout from an invisible cosmic traffic jam. As the mergers ejected material races outward, it might plow into pockets of dense interstellar gas that slow it down abruptly, like a speeding car hitting a wall. The resulting shockwave could take months to build up enough energy to ignite a detectable radio flare. But here's the catch: our best simulations show this process should happen much faster. That leaves physicists scrambling for alternatives. Could the delayed flares come from the merger's remnant, a hypermassive neutron star that refuses to die quietly? Some models suggest these temporary stars spin so fast their magnetic fields become tangled, storing energy that leaks out gradually as radio waves. Others propose wilder ideas like dark matter interactions or even exotic physics from higher dimensions. The truth is, every time we spot another delayed flare, it chips away at our confidence in the standard playbook. These lingering signals might be whispers from a universe operating on rules we haven't discovered yet, reminding us that some cosmic conversations take far longer to decode than we ever imagined. After the cataclysm of a neutron-star collision settles, what's left behind isn't just debris, it's a cosmic oddity spinning at speeds that defy logic. Some of these remnants whirl so fast they flirt with the absolute limits of physics, completing hundreds of rotations every second. Others barely turn at all, lingering in a lethargy that contradicts everything we know about the explosive energy of their birth. This bizarre mismatch, the spin rate mystery, has become one of the most tantalizing windows into the hidden physics of neutron stars. Take the remnant of the merger event GW170817. Based on the energy released during the collision, simulations predicted a rapidly spinning object, likely a neutron star spinning around 1,000 times per minute. But when astronomers analyzed the aftermath, the data suggested something far slower. It's as if the universe slammed the brakes at the last second. Other mergers have left behind remnants spinning too fast, approaching the theoretical maximum where centrifugal forces would rip even ultra-dense neutron matter apart. Neither outcome makes sense if neutron stars behave as we've modeled them. The stakes here are enormous. Spin rates act like fingerprints, revealing secrets about the remnant structure: how rigid or fluid its core is, how tangled its magnetic fields have become. If predictions keep failing, it means we're missing something fundamental about neutron star interiors. One leading theory points to differential rotation, where the star's crust and core spin at wildly different speeds immediately after merging, then suddenly sync up, dumping energy into space like a cosmic clutch engaging. Others argue that magnetic fields, amplified to mind-bending intensities during the collision, might act as hidden anchors, sapping spin energy and redirecting it into jets or radiation. But the wildest possibilities involve states of matter we've never directly observed. Some models suggest the cores of these remnants might temporarily transform into a soup of free quarks, their physics so alien that spin energy dissipates in ways we can't yet calculate. Others speculate that gravitational waves, ripples in spacetime itself, might carry away far more rotational energy than we've accounted for, leaving the remnant sluggish. Every unexplained spin rate is a breadcrumb leading deeper into the labyrinth of extreme physics, hinting that the true nature of neutron stars might be stranger than anything we've dared to imagine. Gravitational waves should be the universe's unmissable signature for neutron star mergers, ripples in spacetime so powerful they shake the very detectors built to find them. Yet sometimes, when telescopes spot the blinding light of a merger, our gravitational wave observatories hear nothing. It's like witnessing an explosion but feeling no blast wave. These silent collisions aren't just odd, they're forcing physicists to question whether we've misunderstood how these cosmic crashes actually unfold. Take the merger detected in 2021 by the Pan-STARRS telescope, a brilliant kilonova over 1 billion light-years away. By all accounts, this cataclysm should have sent gravitational waves surging through LIGO and Virgo's sensitive instruments, but the data came up empty. This wasn't a fluke. Similar, quiet mergers keep appearing in astronomical surveys, each one a puzzle wrapped in enigma. Could the fault lie with our detectors? Maybe current observatories are finely tuned to catch waves within specific frequency ranges, like a microphone deaf to certain pitches. If a merger's gravitational chirp falls outside that window, perhaps because the neutron stars are unusually light or spiral together too slowly, we might miss it entirely. But detector limitations don't explain everything. Some missing waves might stem from the merger's geometry. Gravitational waves aren't emitted equally in all directions. They're strongest along the collision's rotational axis, like the beam of a lighthouse. If Earth happens to be positioned in the equivalent of the lighthouse's shadow, the merger's quiet zone, the signal could slip past us unnoticed. Yet, even accounting for this, statistical models suggest we should have detected far more waves than we have. That gap hints at something stranger, mergers that fundamentally don't behave as we expect. One radical theory suggests these silent events might involve neutron stars with ultra-strong magnetic fields, warping spacetime in ways that suppress gravitational wave production. Another posits that some collisions produce a black hole so quickly, within milliseconds, that the resulting waves get smothered before they can fully develop. Then there's the most mind-bending possibility: mergers where the neutron stars aren't made of ordinary matter at all, but hypothetical exotic particles like strange quark matter, whose collisions might generate waves too faint or high-pitched for our current tech to catch. Every undetected gravitational wave isn't just a failed observation, it's a clue pointing toward gaps in our understanding of neutron stars themselves. As next-generation detectors like the Einstein Telescope and Cosmic Explorer come online, their expanded range might finally decode these cosmic silences. Until then, each missing signal remains a whisper from the universe, reminding us that even the loudest explosions can sometimes keep their deepest secrets quiet. The universe has a heavy element problem, one that starts with neutron star mergers but doesn't end there. These collisions are supposed to be the ultimate cosmic foundries, churning out gold, platinum, and uranium in staggering quantities. Yet when astronomers scan distant galaxies, especially older ones with plenty of merger activity, they often come up empty-handed. It's as if the universe's most prolific factories keep forgetting to ship their products. Take the dwarf galaxy Reticulum 2, a tiny neighbor of the Milky Way. Packed with stars bearing the chemical fingerprints of neutron star mergers, it's swimming in gold and platinum, far more than its size suggests it should have. Meanwhile, larger galaxies like Andromeda show baffling deficits of these same elements despite hosting mergers at similar rates. This isn't just a cosmic accounting error. The disparity hints at something fundamental we're missing about how heavy elements spread or fail to spread after these violent births. One clue might lie in the delivery mechanism. When neutron stars collide, they don't just sprinkle heavy elements gently into space. They blast them outward at nearly the speed of light. In small galaxies with weak gravity, these precious metals might stay trapped close to home, enriching local stars like a closed-loop system. But in massive galaxies, the explosive energy of mergers could eject material entirely, flinging gold and platinum into the intergalactic void before they ever get incorporated into new stars. Then there's timing. The earliest neutron star mergers might have operated differently, occurring in environments so dense their heavy elements sank into galactic centers, vanishing from observable reach. Others could have seeded the cosmos before most galaxies even formed, leaving their metallic legacy diluted across vast stretches of empty space. Compounding the mystery, some elements might hide in plain sight, locked inside neutron-rich compounds so exotic they evade detection by current telescopes. Every mismatched galaxy is a reminder. Even when we catch neutron stars in the act of creating heavy elements, we're still just glimpsing one chapter of a much longer story. Until we unravel how these materials travel, clump, or disappear, the universe's periodic table will keep a few of its heaviest secrets close. Magnetic fields are the hidden puppeteers of neutron star mergers, capable of dictating how these cosmic explosions play out, yet refusing to follow any script we've written for them. In the chaotic moments when two neutron stars collide, their magnetic fields don't just combine, they twist, snap, and reconfigure in ways that defy even the most advanced simulations. Some mergers see fields amplifying to strengths a quadrillion times Earth's, while others mysteriously dampen to near zero. This wild inconsistency isn't just a technicality. It's the reason why some mergers produce dazzling jets and others fizzle out with barely a whimper. Take the case of a merger observed in 2019. As the two stars spiraled inward, their magnetic fields should have tangled into a structured, donut-shaped coil around the collision point, a setup ripe for launching symmetrical jets. Instead, instruments detected a bizarre lopsided field, with one side intensifying explosively while the other seemed to vanish entirely. The resulting jet was so off-kilter it looked like a cosmic firework with half its fizz missing. Then there's the opposite extreme, mergers where magnetic fields grow so strong they essentially strangle themselves, collapsing inward and smothering the very jets they were supposed to power. Why does this matter? Because magnetic fields are the invisible architects of a merger's most dramatic effects. They shape how energy escapes, determine whether gamma-ray bursts will be earth-shattering or feeble, and even influence how heavy elements like gold get forged in the debris. When fields behave erratically, our predictions crumble. For instance, astrophysicists once thought all mergers with strong fields would produce bright, short-lived gamma-ray bursts. But reality keeps delivering curveballs, like the 2022 event where a hyper-strong field produced no gamma rays at all, instead funneling its energy into a bizarre radio afterglow that lingered for months. The root of the problem lies in the incomprehensible conditions inside merging neutron stars. Matter there isn't just dense, it's a turbulent sea of free neutrons, protons, and electrons, all swimming in a soup of quantum uncertainty. Magnetic fields in this environment don't behave like the tidy lines we see around a bar magnet. They fracture into dynamic, fractal-like structures that can reconfigure in microseconds. Some theories suggest these fields might even trigger phase transitions in the neutron star material itself, flipping it between states like a cosmic switch. One moment a solid neutron lattice, the next a fluid of quarks and gluons. Until we crack the code of these magnetic mavericks, every merger remains a roll of the dice. Will the fields align to create a spectacle visible across the universe, or will they conspire to keep the fireworks hidden? The answer might lie in next-generation telescopes designed to map magnetic signatures in real time, or in lab experiments that recreate neutron star conditions here on Earth. Either way, one thing's clear. In the high-stakes drama of neutron star mergers, magnetic fields are the unruly stars of the show. Among the kaleidoscope of cosmic explosions, kilonovae usually paint the universe in fiery reds and oranges, colors that signal the presence of heavy, light-absorbing elements like lanthanum and cesium. But every now and then, these explosions break the mold, shining with an eerie blue hue that shouldn't exist. These blue kilonovae are more than just aesthetic oddities. They're glaring contradictions to our understanding of neutron star mergers, and the clues they hold might rewrite physics itself. The first confirmed blue kilonova appeared in 2017, following the gravitational wave event GW170817. While most of the merger's afterglow faded into the expected red, a stubborn blue component lingered, bright, relentless, and utterly perplexing. Since then, a handful of similar blue outliers have surfaced, each one flaunting a spectrum that screams defiance. Normally, the red color comes from slower-moving, neutron-rich ejecta packed with heavy elements. Blue light, on the other hand, suggests something far hotter and faster material that's either lighter, more energized, or both. So how does a neutron star collision, the ultimate heavy element factory, suddenly start producing this anomaly? One leading theory points to the merger's fast tail, a fraction of the ejected material that gets catapulted outward at velocities approaching 99% the speed of light. This blisteringly fast debris wouldn't have time to form heavy elements, staying instead as a soup of lighter nuclei like helium and oxygen, which glow blue when heated. But here's the catch. Simulations show this material should be vanishingly rare, too sparse to explain the intense blue luminosities we've observed. Unless, of course, neutron star mergers are far messier than we've assumed, flinging out way more of this lightweight material than our models allow. Then there's the more exotic explanation, quark matter. Under the unimaginable pressures of a merger, neutrons might not just break apart. They could dissolve into their constituent quarks, creating a fleeting state of matter unlike anything in our universe today. If even a tiny fraction of the neutron star's core transforms into this quark-gluon plasma during the collision, it could release a surge of energy that superheats the surrounding ejecta, forcing it to shine blue. Some physicists speculate that these blue kilonovae might be our first indirect evidence of quark nova explosions where quark matter itself becomes the powerhouse. But the plot thickens further. A radical third idea suggests that blue kilonovae might come from mergers involving a special class of neutron stars, ones born with unusually low masses or strange magnetic field configurations. These lightweight neutron stars could produce cleaner, less neutron-rich debris when they collide, resulting in faster, hotter outflows that naturally favor blue emission. If true, it would mean the universe has been hiding an entire subcategory of neutron stars right under our noses, ones that only reveal themselves through these cryptic blue outbursts. Yet for all the theories, one fact remains glaringly obvious. Blue kilonovae shouldn't be this bright, this persistent, or this rare. Their very existence implies gaps in our knowledge, perhaps in how ejecta interacts with magnetic fields, how turbulence distributes energy during a merger, or even how fundamental particles behave under conditions we can't replicate on Earth. Every blue-hued outlier is a cosmic flare in the dark, illuminating just how much we still have to learn about the universe's most violent rendezvous. When neutron stars merge, the aftermath should be inevitable, a catastrophic collapse into a black hole within milliseconds. The math is clear. Cram two ultra-dense stellar corpses together, and gravity should win instantly. Yet somehow, against all odds, some mergers spit out a temporary survivor, a bizarre, overstuffed neutron star that refuses to die. These hypermassive remnants spin wildly, bloated with more mass than any single neutron star should hold, teetering on the edge of collapse. But not crossing it. How the answer might rewrite our understanding of matter itself. Take the merger event GW170817. For nearly a second, an eternity in merger time, its remnant pulsed as a hypermassive neutron star defying gravitational doom. Simulations suggest it shouldn't have lasted longer than a blink, but here's the twist: rapid rotation isn't the only thing keeping these stellar zombies alive. Under normal circumstances, even the fastest spin would be no match for the crushing weight of excess mass. The real secret might lie in a phenomenon called differential rotation, where the star's core and outer layers spin at drastically different speeds. This creates an internal tug-of-war, with centrifugal forces in the outer layers counteracting the inward pull of gravity at the core, like a cosmic spinning top that stabilizes itself through sheer chaos. But there's another player in this balancing act: the unfathomable strength of neutron star matter. At these densities, protons and electrons merge into neutrons, creating a quantum soup where particles resist compression with unbelievable force. Some theories suggest hypermassive remnants might push this material into an even stranger state, perhaps a fleeting form of quark matter, where neutrons dissolve into their fundamental particles. This phase change could temporarily stiffen the star's interior, buying precious extra milliseconds before collapse, yet the clock is always ticking. Even these extreme mechanisms can't stave off gravity forever. Eventually, energy bleeds away through gravitational waves, magnetic braking, or violent eruptions, and the hypermassive star succumbs. But that delay isn't just a cosmic curiosity. It's a window into physics we can't replicate on Earth. The longer these remnants linger, the more they reveal about the absolute limits of matter's ability to resist annihilation. Every extra millisecond of existence is a defiance of the universe's rules, a reminder that even in the face of oblivion, matter finds ways to fight back. Neutrinos are the universe's stealthy escape artists, particles so ghostly they can pass through entire planets without a single interaction. When neutron stars collide, the unimaginable pressures and temperatures should unleash a tsunami of these elusive particles, flooding space with trillions of them every second. Yet when scientists point their detectors at these cosmic smash-ups, they often come up disturbingly empty-handed. The missing neutrinos are more than an observational hiccup. They're a glaring mismatch between theory and reality that could force us to rewrite the physics of these catastrophic events. Take the historic merger GW170817. Based on the energy released, neutrino observatories like IceCube and Super Kamiok, and should have recorded a spike in detections, neutrinos slamming into Antarctic ice or Japanese water tanks with unmistakable signatures. Instead, the data showed nothing beyond background noise. This wasn't a one-off fluke. Of the handful of neutron star mergers we've observed, fewer than half have produced detectable neutrino bursts. If these collisions are supposed to be neutrino factories, why is the assembly line shutting down without warning? One possibility cuts straight to the heart of our models. Maybe we've overestimated how many neutrinos these mergers actually produce. Current simulations assume neutron star material, when heated to trillions of degrees, will emit neutrinos as freely as the sun emits light. But what if the debris is far more opaque to these particles than we've guessed? In the chaotic aftermath of a merger, the ejected material might form dense, swirling clouds that trap neutrinos instead of releasing them, like fog absorbing a flashlight beam. Then there's the wild card of directionality. Neutrinos aren't emitted evenly in all directions. They're channeled along magnetic field lines or concentrated in jets, much like the plasma beams we see in gamma-ray bursts. If Earth isn't in the path of a neutrino jet, we'd miss the signal entirely. Some theorists even suggest that neutrino emission could be suppressed entirely in certain mergers. Perhaps those producing short-lived hypermassive neutron stars whose rapid rotation diverts energy into gravitational waves instead. But the most tantalizing explanation might lie beyond the standard model. What if neutrinos from neutron star mergers are transforming into an undetectable form along the way? Certain extensions to particle physics predict sterile neutrinos, heavy, shadowy variants that don't interact with matter at all. If a fraction of the neutrinos emitted during a merger oscillate into these invisible states, our detectors would only catch a fraction of the expected signal. Every absent neutrino burst forces us to reconsider what we think we know about these collisions. Are we misjudging the conditions inside merging neutron stars, missing key physics in our simulations, or staring straight at hints of particles we've never seen? Until we solve this cosmic hide-and-seek game, these silent mergers will keep whispering a frustrating truth. Even the universe's most violent explosions can leave their faintest fingerprints just out of reach. The debris from neutron star mergers isn't just flung into space, it's catapulted with such ferocity that some of it breaks the cosmic speed limit. Under normal physics, the fastest material ejected during these collisions should top out around 70% the speed of light. Yet time and again, telescopes catch streams of debris racing impossibly faster, as if propelled by some hidden cosmic slingshot. This ejector speed mystery isn't just a quirk of observation. It's a direct challenge to our understanding of how matter behaves when pushed to the brink of annihilation. Take the aftermath of the merger event GW190425. Spectroscopic analysis revealed atomic signatures indicating some material had reached 94% light speed, far beyond what simulations predicted. Even more baffling, this wasn't isolated to a few stray particles. Entire clumps of neutron-rich matter were clocked moving in unison at these ludicrous velocities, defying the laws of hydrodynamics that say such dense material should decelerate rapidly. If our models are correct, this shouldn't be possible without an unknown energy source acting like an afterburner for the debris. The leading explanation points to magnetic fields, but not just any magnetic fields. During a merger, the chaotic tangle of the star's magnetic lines might reconfigure into vast flux tubes, structures that function like particle accelerator beams channeling energy into select pockets of debris. Think of it like squeezing a water hose to make the stream shoot farther. Magnetic pressure could focus energy into narrow jets of ejector, accelerating them beyond standard limits. But there's a catch. For this mechanism to work, the fields would need strengths exceeding any ever observed in nature, nearly 10 to the 16th power Gauss, or 1,000,000 times more intense than typical neutron stars. Then there's the wild card of phase transitions. At the moment of collision, neutron star matter might briefly transform into exotic states, like quark-gluon plasma releasing stored energy in sudden bursts that kick surrounding debris to relativistic speeds. Some theorists even speculate about temporary viscosity drops, where the merging material becomes eerily frictionless for microseconds, allowing ejector to slip free with minimal drag. But the most provocative possibility, these speed violations might hint at physics beyond general relativity. Certain modified gravity theories predict spacetime itself could become elastic during extreme events, creating temporary slingshot zones where ejector gains extra momentum. It's as if the universe, for the briefest instant, relaxes its own rules just to keep us guessing, until we catch one of these runaway debris clouds in the act, or simulate conditions extreme enough to replicate them. Every ultrafast particle remains both a puzzle and an invitation to rethink the limits of cosmic violence. Gamma-ray bursts are the universe's most violent flashes, cosmic detonations so bright they can outshine entire galaxies in a heartbeat. Yet when these bursts follow neutron star mergers, their durations spin wildly out of control, defying every pattern we thought we knew. Some last a fraction of a second blink and you'll miss them. Others stretch for minutes as if time itself has slowed down in the chaos. This isn't just random variation. It's a screaming clue that something fundamental is missing from our understanding of how these collisions unfold. Take the gamma-ray burst GRB211211A, detected in 2021. Clocking in at nearly 50 seconds, it shattered expectations for neutron star mergers, which typically produce bursts under 2 seconds. The event's afterglow pointed squarely to a merger origin, yet its duration matched those usually seen when massive stars collapse into black holes, a scenario with entirely different physics. Then there's the opposite extreme, bursts like GRB 180618A, which flickered out in just 0.2 seconds. If both came from neutron star collisions, why does one linger like a dying ember while the other vanishes like a snuffed flame? The key might lie in what's left behind after the merger. Picture the collision's aftermath as a cosmic demolition derby, where the debris forms a swirling, superheated disk around either a newborn black hole or a hypermassive neutron star. In the black hole scenario, matter falls inward almost immediately, powering a jet that cuts off abruptly, resulting in a short burst. But if the remnant is a rapidly spinning neutron star, its magnetic fields can act like a throttle, steadily feeding material into the jet and stretching the burst's duration. The problem: some ultra-long bursts show no evidence of a neutron star remnant at all, while some short bursts coincide with mergers where a neutron star clearly survived. Enter the wild card, the merger's environment. Neutron stars don't collide in empty space. They're often surrounded by gas ejected during their death spiral. If this material is dense enough, it can choke the jet, forcing it to burrow outward like a tunnel through sludge. The longer the struggle, the more prolonged the burst. Alternatively, if the stars merge in a near vacuum, the jet might escape unimpeded, resulting in a brief flash. There's also the spin factor. When neutron stars orbit each other hundreds of times per second before merging, their tidal forces can shred them asymmetrically, producing messy debris clouds that irregularly fuel or starve the jet. But the most tantalizing possibility involves magnetic fields gone rogue. Simulations suggest that in certain mergers, magnetic instabilities might fracture the jet into pulsating knots of energy. Some knots could lag behind others, arriving at Earth minutes apart and fooling telescopes into seeing a single, drawn-out burst. Other mergers might produce jets that flicker like a faulty neon sign, their uneven power delivery masquerading as a shorter burst. Until we catch these processes in real time, or simulate them with quantum-level precision, every gamma-ray burst duration remains a cosmic Rorschach test, revealing as much about our model's flaws as it does about the mergers themselves. Some neutron star mergers play a cosmic game of hide and seek, announcing their existence with ripples in space-time while leaving telescopes staring at empty blackness where light should be. These dark mergers spit out gravitational waves strong enough to rattle detectors on Earth, yet produce no electromagnetic counterpart. No gamma-ray burst, no kilonova glow, not even a flicker of radio waves. It's as if the universe is hosting the most violent parties imaginable, then turning off all the lights before anyone can peek inside. Take the gravitational wave event GW190514. When LIGO and Virgo picked up its signal in 2019, observatories worldwide swung into action, scanning the predicted region of space. Days passed, then weeks. Nothing. The merger had all the hallmarks of a neutron star collision: the frequency, the duration, the energy, yet left behind no trace of light. Similar dark events now account for nearly 20% of suspected neutron star mergers, posing a glaring question: what's keeping these cosmic crashes so eerily invisible? One possibility plunges us into the realm of exotic stellar corpses. Ordinary neutron stars aren't the only dense objects lurking in the cosmos. There might be stranger siblings hiding in the dark. Theoretical quark stars, for instance, could form when neutron stars compress beyond their breaking point, collapsing into even denser spheres of pure quark matter. If two quark stars merge, their collision might dump energy directly into gravitational waves and neutrinos, skipping the electromagnetic fireworks entirely. Then there's the speculative prion star hypothesis, where mergers involve objects made of hypothetical subquark particles, generating gravity waves without any standard luminous debris. But exotic stars aren't the only explanation. Dark mergers might simply occur in the universe's worst neighborhoods, regions so clogged with gas and dust that any light gets smothered at birth. Picture a neutron star binary orbiting deep inside an active galactic nucleus, where thick clouds of molecular gas swirl around a supermassive black hole. When the stars finally merge, their explosion would be buried under layers of obscuring material, like a firework detonating inside a lead box. Supporting this idea, several dark events trace back to galaxies with unusually high star formation rates, environments notorious for their dense, light-absorbing nebulas. The plot thickens with mergers involving black holes. While LIGO routinely detects black hole collisions, some signals sit in a gray zone, masses too light for typical black holes but too heavy for textbook neutron stars. These mass gap objects might be neutron stars that collapsed into black holes milliseconds before merging, creating a hybrid event where the gravitational wave signature resembles a neutron star collision, but the lack of matter leaves no light to observe. Alternatively, they could be primordial black holes, those hypothesized relics from the Big Bang colliding with neutron stars in near total darkness. The implications ripple beyond mere curiosity. If dark mergers truly involve quark stars or other exotic objects, their existence would rewrite our understanding of nuclear physics under extreme conditions. Confirming even one would require detectors sensitive enough to spot subtle differences in their gravitational wave chirps, perhaps a telltale vibrational frequency hinting at quark matter's unique properties. On the flip side, if obscuring environments explain most dark events, it means we're chronically underestimating the merger rate in dusty galaxies, skewing our cosmic census of heavy element production. Every lightless merger forces us to confront just how much of the universe's violence might be happening in the shadows. As gravitational wave astronomy advances, these dark events could become our most valuable anomalies, silent messengers revealing physics too strange or environments too extreme for conventional astronomy to spot. Until then, each one remains a ghostly signature on our detectors, whispering that some of the cosmos's most spectacular crashes prefer to keep their curtains drawn. X-ray telescopes should have a front-row seat to neutron star mergers, cataclysms so violent they light up the high-energy spectrum like cosmic fireworks. But sometimes, long after the initial explosion fades, these observatories catch something bizarre. X-ray flares reigniting weeks or even months later, like embers bursting back to life in a cold fireplace. These delayed afterglows aren't just unexpected, they're outright contradictory to how we thought these mergers behaved. If all the energy gets blasted outward in the first seconds, what's powering these lingering X-ray encores? Take the merger event GW170817. After its gravitational waves and Kilonova faded, the Chandra X-ray Observatory kept watching. For 2 weeks, nothing. Then suddenly, an X-ray flare brighter than the entire Milky Way galaxy flared to life, lasting nearly 4 months before vanishing. Standard models predicted the merger's X-ray emission should have peaked within hours, powered by shockwaves from the initial explosion. This late surge made no sense, as if the debris had a hidden battery slowly releasing energy. Similar flares have since popped up in other mergers, each one a cosmic whodunit with 2 prime suspects: a zombie neutron star refusing to die, or invisible gas clouds playing cosmic pinball with the wreckage. The zombie star theory is particularly spine-tingling. When neutron stars merge, they don't always collapse straight into a black hole. Sometimes they form a temporary hypermassive neutron star, spinning so fast its centrifugal force staves off collapse. These stellar undead might pulsate for minutes, hours, or even days before finally succumbing to gravity. During this grace period, their absurdly strong magnetic fields could channel leftover rotational energy into focused beams, particle accelerators on a cosmic scale. If one of those beams happens to point at Earth, we'd see it as a delayed X-ray flare, flickering as the star's spin gradually slows. But there's a catch. These flares often last far longer than any known hypermassive neutron star should survive, suggesting either our lifespan estimates are wildly off or something even stranger is at play. That's where the cosmic pinball scenario comes in. Imagine the merger ejector, a cloud of ultra-hot, neutron-rich debris, slamming into interstellar gas that drifted too close. The collision would generate shockwaves, heating the gas to X-ray temperatures. But here's the twist. If that surrounding material is clumpy or distributed unevenly, the ejector might hit pockets of gas at different times, creating staggered bursts of X-rays. It's like throwing a handful of gravel into a pond. Some ripples arrive immediately, while others bounce off hidden rocks and show up late, but the plot thickens. Some X-ray afterglows pulse rhythmically, like a lighthouse beam sweeping past Earth every few hours. This regularity points to a central engine, possibly a black hole slurping down debris from a surrounding disk. As material spirals inward, magnetic fields could fling portions of it outward at relativistic speeds, creating X-ray jets that flicker as the disk wobbles. The real mystery: why these feeding frenzies sometimes take weeks to start. One radical idea suggests the disk might initially be too cool to emit X-rays, only flaring up once enough material piles up to reach critical temperatures. Every delayed X-ray flare is a breadcrumb leading deeper into the labyrinth of merger physics. Are we seeing the final death throes of magnetized stellar remnants? Or watching shockwaves plow through hidden gas reservoirs light years across? The answer might reshape how we understand not just neutron star mergers, but the invisible environments where these cosmic dramas unfold. Until then, each unexpected afterglow remains a tantalizing hint, proof that even when we think the show's over, the universe might just be waiting to take a bow. Simulations paint neutron star mergers as elegant cosmic ballets, a symmetrical explosion sending debris flying in smooth, predictable clouds, but reality loves a mess. When telescopes zoom in on these collision sites, they don't see orderly halos of ejecta. Instead, they catch chaotic splatters, twisted ribbons, and bizarre clumps of material flung in all directions. This isn't just random cosmic graffiti, it's evidence that something powerful and poorly understood is sculpting these debris fields into shapes that defy our cleanest models. Take the merger GW170817. High-resolution imaging revealed its ejecta wasn't a uniform shell but a lopsided spray, with dense knots of material clustered along one side like beads on a broken necklace. Even more puzzling, some clumps moved significantly slower than others, as if an invisible hand had braked them mid-flight. Similar asymmetries keep appearing in other mergers, from jagged crescents to spiraling tendrils of hot gas. If neutron star debris were simply exploding outward like shrapnel, we'd expect smooth distributions. These fragmented structures suggest hidden forces at work, and the prime suspects are turbulence and magnetism, locked in a cosmic tug of war over how the wreckage settles. Turbulence in this context isn't just random chaos. During a merger, the unimaginable pressures create whirlpools of plasma hotter than the sun's core, spinning at velocities approaching light speed. These vortices can stretch and tear ejecta into strands, much like cream swirling into coffee, except here, the cream is neutron-rich matter dense enough to crush atoms into submission. Some simulations now suggest that when two neutron stars first collide, their outer layers don't just merge, they slosh violently, creating internal shockwaves that fragment the debris before it even escapes. Picture shaking a soda can and then prying it open. The erupting foam wouldn't be smooth but foamy and irregular. Now magnify that to stellar scales and you've got a recipe for cosmic splatter art. But turbulence alone can't explain the most extreme ejecta shapes. Enter magnetism's hidden hand. Neutron stars boast the strongest magnetic fields in the universe, so intense they can rearrange matter at the atomic level. During a merger, these fields don't just vanish, they snap, twist, and reconnect in ways that could mold ejecta like cosmic Play-Doh. Imagine squeezing a tube of toothpaste, only for the paste to suddenly curve midair because invisible magnets are pulling it sideways. That's the kind of sculpting power we're dealing with. Some observations even hint at magnetic filaments, thin, thread-like structures in the debris, where fields have channeled material into eerie, elongated shapes resembling celestial spiderwebs. The wildest possibility, these asymmetries might encode secrets about the merger's very first moments. Just as a shattered vase's fragments reveal how it hit the floor, the clumps and gaps in merger ejecta could trace the exact sequence of the star's destruction. For instance, if one neutron star was slightly more massive than the other, its gravity would dominate during the final death spiral, skewing debris toward one side. Alternatively, if the stars had wildly different magnetic field orientations, their clash might have launched ejecta in preferential directions like cosmic shrapnel. Even the spin axes of the original stars could leave fingerprints in the debris pattern, a celestial cold case waiting to be cracked. What makes this mystery so urgent is its ripple effect. Ejecta shapes directly influence how heavy elements spread through space. Smooth clouds would distribute gold and platinum evenly, like fertilizer tilled into soil. Clumpy ejecta, though, might concentrate these precious metals into cosmic nuggets, dense pockets that could seed future generations of stars and planets unevenly. There's even a chance we're seeing echoes of these irregularities in our own solar system's composition, where certain heavy elements appear curiously clustered. Every twisted ribbon of debris forces us to reconsider not just how neutron stars die, but how their remains go on to build new cosmic landscapes, one messy, glorious splatter at a time. After the chaos of a neutron-star merger settles, one of two things should remain: either a black hole or a rapidly spinning pulsar sending out rhythmic beams of radiation like a cosmic lighthouse. But here's the cosmic conundrum. While we've spotted plenty of black holes left behind by these collisions, the expected pulsars are conspicuously absent. If mergers produce them as often as theories suggest, where are they all hiding? This missing pulsar problem isn't just an observational hiccup. It's a direct challenge to our understanding of how neutron stars are reborn in the wake of catastrophe. Consider the aftermath of the merger GW170817. Based on the energy released and the masses involved, simulations gave it a 40% chance of leaving behind a pulsar rather than a black hole. Yet when radio telescopes scoured the collision site for months afterward, they found no telltale pulses, just silence. The same pattern holds for nearly every other merger we've studied. Statistically, we should have detected at least a handful of these spinning remnants by now. Instead, the cosmos seems to be hoarding them, leaving astronomers to wonder, are these pulsars simply too shy, or are our models missing something fundamental? One compelling theory suggests these newborn pulsars might be drowning in their own debris. When neutron stars merge, they eject vast clouds of material, some moving fast, some slow, that can linger for years. If a pulsar forms inside this shroud, its radio beams could be scattered or absorbed before reaching us, like a flashlight smothered by thick fog. Supporting this idea, several merger sites show lingering infrared glows consistent with dense debris clouds. But here's the catch: debris alone can't explain why we don't see even a flicker of pulsation breaking through. Unless, of course, the material isn't just obscuring the pulsar, it's actively choking it. That's where magnetic fields enter the picture. During a merger, magnetic energies skyrocket to levels that make neutron star factories look tame. If these fields become tangled enough, they could trap the pulsar's emission entirely, wrapping it in a cage of invisible force lines. Some theorists speculate these magnetic tombs might redirect the energy inward, heating the star's surface until it shines in X-rays instead of radio waves, a stealth mode that would evade traditional pulsar hunts. There's precedent for this. Magnetars, neutron stars with ultra-strong fields, often skip predictable pulses in favor of erratic X-ray outbursts. Could merger-born pulsars be their even more secretive cousins? Then there's the ticking clock scenario. Maybe these pulsars aren't missing, they're just dying young. The hypermassive neutron stars left after some mergers might spin down catastrophically fast, their magnetic fields sapping rotational energy so efficiently that they fade from detectable pulses within months. Gravitational waves could play a role too, carrying away so much spin energy that the pulsar stumbles into oblivion before telescopes can catch its rhythm. If this is true, we might need ultra-rapid response campaigns catching mergers within days rather than weeks to spot these fleeting cosmic heartbeats. But the most unsettling possibility, some mergers might not make pulsars at all. If the colliding stars are asymmetric enough, say, one loaded with dark matter or exotic quark matter, their merger could produce a brief, unstable remnant that quietly implodes without ever settling into a pulsar's steady spin. Alternatively, the collision might trigger a phase transition, converting the neutron star into an entirely new state of matter that doesn't pulse predictably. Every undetected pulsar is a quiet nudge, hinting that the universe's recipe for stellar rebirth might have ingredients we haven't even imagined yet. Until we catch one of these elusive spinners in the act, their absence will loom over merger science, a silent reminder that even the loudest cosmic crashes can leave behind whispers we're still learning to hear. When astronomers point infrared telescopes at neutron star mergers, they expect to see a specific pattern, a kilonova's glow fading steadily as heavy elements like lanthanum and cesium absorb visible light and re-emit it at longer infrared wavelengths. But some kilonovae break the rules, blasting out far more infrared radiation than the models predict. This infrared excess isn't just a minor discrepancy. It's a glaring sign that somewhere in the chaotic aftermath of these collisions, unknown materials are lurking, or physics is playing by a different set of rules. Take the kilonova at 2017 GFO, the electromagnetic counterpart to GW 170817. While its visible light faded as expected, its infrared emission stubbornly lingered, staying bright for weeks beyond predictions. The same anomaly appeared in 2022 with GRB 211211A, where the infrared glow outshone theoretical estimates by a factor of 10. These aren't isolated flukes. Roughly 1 in 3 kilonovae now show this mismatch, forcing astrophysicists to confront an unsettling truth. Our models of merger ejecta might be missing entire chapters. One leading theory blames the excess on an unexpected ingredient in the debris lightweight elements like helium or carbon, which shouldn't be abundant in neutron-rich environments. When neutron stars collide, most of the ejected material is so dense it rapidly forms heavy elements through the R process. But if a fraction of the debris gets heated to extreme temperatures without capturing extra neutrons, it could remain as lighter atoms. These lighter elements emit infrared more efficiently than their heavier counterparts, potentially explaining the surplus glow. The catch: simulations struggle to produce enough of this lightweight material to match observations unless neutron stars are far less neutron-rich at their surfaces than we've assumed. Then there's the dust hypothesis. Imagine the merger ejecta still searingly hot, plowing into pre-existing dust clouds in the interstellar medium. The collision would heat those dust grains, making them radiate intensely in the infrared. This could explain why some kilonovae show delayed infrared excesses. The ejecta takes time to reach distant dust. But critics point out that many mergers occur in relatively clean regions of space where dense dust clouds shouldn't be lurking. Unless, of course, neutron stars themselves shed dusty shrouds before merging, a possibility no model currently accounts for. The wildest explanations venture into exotic physics. Some theorists suggest the infrared excess could come from strangelets, hypothetical nuggets of strange quark matter that might form fleetingly during the merger. These particles, if they exist, could decay by emitting unusual infrared signatures. Others propose that strong magnetic fields in the ejector might twist the paths of emitted photons, redshifting them into the infrared en masse. There's even speculation that certain heavy elements like tellurium or iodine could form metastable compounds under merger conditions, releasing energy in infrared wavelengths we haven't yet catalogued. What makes this puzzle so urgent is its ripple effects. Infrared emission isn't just a curiosity, it's a key tracer of how heavy elements disperse. If we're misjudging the physics behind this glow, we might also be misreading the cosmic distribution of gold, platinum, and other R-process treasures. Every anomalous kilonova forces us to reconsider whether the universe's chemical factories are running on hidden settings, churning out elements in ways we've yet to fathom. Until we crack the code of these infrared rebels, each excess remains a beacon, illuminating just how much we still have to learn about the aftermath of the cosmos's most violent embraces. Gravitational wave detectors like LIGO and Virgo usually record neutron star mergers as single, unmistakable chirps, short bursts of spacetime ripples that rise in frequency before cutting off abruptly. But buried in the data from a handful of events, some researchers claim to have detected something far stranger, faint, repeating echoes of the original signal, arriving seconds or even minutes later. If real, these gravitational wave reverberations would upend our understanding of what happens during and after these cosmic collisions. The implications are staggering, from evidence of exotic quantum spacetime effects near newborn black holes to flaws in our detectors we never anticipated. The first hints emerged from reanalysis of GW 170817's data. Beyond the primary chirp, independent researchers reported statistically significant post-merger oscillations, tiny blips following the main event at precise intervals like a bell's lingering ring. Other teams soon claimed similar echoes in older black hole merger data, suggesting the phenomenon might not be unique to neutron stars. Skeptics fired back immediately, noting that random noise in the detectors could mimic such patterns through sheer coincidence. The controversy highlights a fundamental challenge. Gravitational wave astronomy is still in its infancy, and separating true signals from artifacts requires near superhuman precision. One tantalizing explanation for real echoes involves nascent black holes behaving like cosmic drums. According to some fringe theories, a freshly formed black hole's event horizon might vibrate at specific frequencies as it settles into equilibrium, emitting gravitational ripples with each oscillation. These quasi-normal modes would theoretically produce delayed, attenuated copies of the original merger signal. The catch: for neutron star mergers, the predicted echoes should be far too weak for current detectors to spot, unless some exotic physics amplifies them. That's where ideas like quantum gravitational effects or fuzzballs, hypothetical alternatives to black holes with surface structure, enter the picture, offering mechanisms to boost the echo's strength. But the plot twists further when considering the detectors themselves. LIGO laser beams don't travel through perfect vacuum. Tiny fluctuations in air pressure, seismic vibrations, even thermal noise in the mirrors could create false echoes. One study suggested that photon scattering in the interferometer's arms might produce delayed signal artifacts mimicking real echoes. Others point to nonlinear detector responses, where an extremely loud main event temporarily skews the instrument's sensitivity, causing it to ring like an overloaded microphone. The debate remains unresolved, but next-generation detectors like the Einstein telescope could settle it, with sensitivity improvements up to 10 times greater than current observatories. They'll either confirm these whispers from the edge of physics or expose them as the universe's most elaborate false alarms. Until then, every claimed echo lingers in the realm between groundbreaking discovery and cosmic mirage, reminding us that even our most advanced tools still struggle to hear the universe clearly. The universe has a habit of blurring the lines between cosmic categories nowhere more clearly than in the mysterious mass gap that supposedly separates neutron stars from black holes. For decades, astrophysics textbooks drew a neat boundary. Neutron stars top out around 2.2 times the Sun's mass, while black holes start at roughly 5 solar masses. The gap in between was considered a no-man's land, physically forbidden by the laws of stellar collapse. But when gravitational wave detectors started eavesdropping on neutron star mergers, they began catching whispers of objects that shouldn't exist, remnants straddling this forbidden zone with no regard for our tidy classifications. Take the collision GW1 90425 detected in 2019. The event's gravitational waves revealed a final remnant weighing in at 3.4 solar masses smack in the middle of the mass gap. Similar outliers keep appearing in the data, each one a cosmic rebel refusing to fit either category. If these objects are neutron stars, their sheer mass should have crushed them into black holes instantly. If they're black holes, they're inexplicably tiny, flouting the known pathways for black hole formation. This isn't just a minor accounting error, it's a fundamental challenge to how we define the densest objects in existence. The implications ripple across astrophysics. One possibility is that our mass limits were wrong all along, that neutron stars can, under extreme conditions, cling to stability beyond their supposed breaking point. Simulations now suggest that rapid rotation might act like cosmic glue, allowing hypermassive neutron stars to temporarily resist collapse even when packed with 3 or 4 solar masses. But these ultra-spinning survivors should be fleeting, lasting seconds at most before succumbing to gravity. Yet some mass gap objects seem to endure for years, implying either unknown stabilizing mechanisms or a radical revision of neutron star physics. Then there's the black hole paradox. Conventional wisdom says black holes can't form below 5 solar masses because collapsing stars shed too much mass in supernova to leave smaller remnants behind. But what if some neutron star mergers bypass this rule entirely? When 2 neutron stars collide, their combined mass might teeter on the edge of collapse without the explosive mass loss of a supernova, creating lightweight black holes that slip into the gap. Even stranger, some theories propose primordial black holes. Those hypothetically forged in the Big Bang's chaos could lurk in this mass range, occasionally merging with neutron stars and muddying the waters further. The wildest explanations lurk in the realm of exotic matter. Certain quantum gravity models predict that under merger-level pressures, neutron star material might transform into bizarre states like strange quark matter or Bose-Einstein condensates, creating hybrid objects with properties of both neutron stars and black holes. These theoretical quark stars, or gravastars, could occupy the mass gap comfortably, masquerading as one or the other depending on how we observe them. Every mass gap detection forces us to confront an uncomfortable truth. The universe doesn't care about our classification schemes. As detectors grow more sensitive, these enigmatic outliers may prove to be the rule rather than the exception, hinting that the cosmic family of compact objects is far stranger and more diverse than we ever imagined. Until we solve this puzzle, each merger that defies the gap stands as a humbling reminder. Nature's playbook has pages we haven't even begun to read. The merger known as GW1 90425 wasn't just another cosmic collision, it was a heavyweight bout that shattered expectations. When LIGO and Virgo detected its gravitational waves in 2019, the data told a story no one had fully anticipated. 2 neutron stars, each roughly 1.9 times the mass of our Sun, spiraling into oblivion. That combined mass, nearly 3.8 solar masses, shouldn't have been possible under conventional stellar physics. Neutron stars aren't supposed to get that big. Yet here was the universe, casually serving up a pair of cosmic anomalies that forced astrophysicists back to the drawing board. What makes this merger so perplexing isn't just the sheer heft of its participants, but where they likely came from. Most neutron star pairs we've observed tip the scales at a combined 3 solar masses or less, their origins traced back to relatively placid binary star systems. GW190425's duo, however, points to a far more violent backstory. One leading theory suggests these bruisers might have started life as massive stars locked in a tight orbit, their evolution warped by intense mutual interactions. As the stars aged and shed material, their outer layers could have mixed unpredictably, leaving behind cores packed with extra mass. Alternatively, they might have formed separately in dense stellar environments like globular clusters, where gravitational encounters could have shoved them together long after their birth. But the real shock came after the merger. Simulations predicted such massive neutron stars would collapse instantly into a black hole, their combined gravity too overwhelming to resist. Yet the gravitational wave signal hinted at something stranger, a remnant lingering just long enough to suggest a brief, hypermassive neutron star might have formed before the final plunge. This fleeting survivor, if real, would have spun hundreds of times per second, its core compressed to densities where even neutrons might dissolve into a soup of quarks. The implications ripple across astrophysics. If neutron stars can grow this massive and still resist collapse even briefly, our models of their internal structure and the very nature of ultra-dense matter might need a radical rewrite. The echoes of GW190425 extend beyond the merger itself. Its existence implies there could be an entire population of overweight neutron stars hiding in the cosmos, invisible to conventional telescopes until they collide. Some might be lurking in the debris fields of ancient supernovae, their birth shrouded in violence. Others could be the products of earlier, unseen mergers, stellar phoenixes risen from previous collisions to collide again. Every outlier like this forces us to reconsider not just how neutron stars form, but how they evolve in the shadows. Perhaps most tantalizing is what this event says about the origins of heavy elements. With so much mass concentrated in one system, the merger's ejecta would have been exceptionally rich in neutrons' prime conditions for forging gold, platinum, and other R-process elements. Yet follow-up observations found curiously muted chemical signatures, as if the explosion held back some of its cosmic bounty. This mismatch hints that the heaviest neutron stars might operate by different rules, their collisions producing elemental yields that don't fit the standard mold. GW190425 stands as a cosmic cautionary tale, a reminder that the universe doesn't play by neat categories. For every rule we devise about stellar mass limits or merger outcomes, there's an exception waiting in the wings, ready to upend our assumptions. As detectors grow more sensitive, these outliers may prove to be not rare flukes, but members of a hidden demographic we're only beginning to glimpse. Until then, this heavyweight collision remains a benchmark, challenging us to rethink what neutron stars can and cannot be. Some neutron star mergers don't just announce their arrival, they send cryptic warnings first. Minutes or even hours before the main gravitational wave crash, telescopes occasionally catch strange precursor flares, bursts of X-rays or gamma rays flashing like distant beacons, hinting that something catastrophic is about to unfold. These early signals shouldn't exist according to standard models, which predict mergers should unfold in silence until the final, violent embrace. Their very presence suggests the stars might be communicating in ways we're only beginning to decipher, revealing hidden dynamics in the moments before annihilation. Take the merger GW150914, detected in 2015. Nearly half an hour before LIGO registered the gravitational waves, the Fermi Gamma Ray Space Telescope recorded a faint 2-second gamma-ray blip from the same patch of sky. Statistically, the odds of this being a coincidence were less than 1 in 1,000. Similar precursors have since surfaced in other events, each one a fleeting glimpse into the merger's prologue, a cosmic countdown we never knew to watch for. The question isn't just whether these flashes are real, but what could possibly trigger them when the stars are still thousands of miles apart. One leading theory points to the stars' magnetospheres, the invisible webs of magnetic force surrounding them. As neutron stars spiral closer, their magnetic fields don't just sit idle, they stretch, tangle, and occasionally snap like overstretched rubber bands. When these field lines reconnect, they could unleash torrents of energy, accelerating particles to near light speeds and producing the observed X-ray or gamma-ray sparks. Imagine two magnets spinning wildly as they approach each other, sporadically flinging off sparks as their forces clash, except here, the sparks are high-energy radiation potent enough to cross interstellar space. But there's a catch. For precursor flares to reach Earth, the magnetic reconnection would need to occur along our line of sight, which seems improbably convenient unless these events are far more common than we've detected. That's where the wilder explanations come into play. Some models suggest tidal forces in the final orbits might squeeze the star's crust violently enough to trigger localized starquakes, cracking their ultra-dense surfaces and unleashing bursts of radiation. Others speculate about unstable mass transfer, where one neutron star begins shedding material onto its companion in erratic, explosive surges before the final merger. The stakes go beyond mere curiosity. If precursors are real, they could revolutionize how we observe mergers. Currently, gravitational wave detectors provide mere seconds of warning before the main event, leaving telescopes scrambling to catch the aftermath. Precursor flares, if predictable, might offer precious hours to point instruments in the right direction, capturing the merger's earliest moments in unprecedented detail. But first, we need to confirm they're not just cosmic false alarms, glitches in detectors, or unrelated flashes masquerading as harbingers. The solution might lie in next-generation observatories. Upcoming satellites like the Einstein probe, designed to monitor X-ray transients with unmatched sensitivity, could finally settle the debate by catching precursors in the act. Until then, every mysterious pre-merger flash remains a tantalizing what-if, a whisper from the stars that they might be louder and stranger in their final hours than we ever imagined. Imagine the cosmic frustration gravity wave detectors blare with the unmistakable chirp of colliding neutron stars, yet when telescopes swing into position, they find nothing. No flash of gamma rays, no glowing kilonova, just empty darkness where light should be. These missing optical counterparts aren't just failed observations, they're cosmic riddles wrapped in interstellar dust and exotic physics. Why do some mergers scream across the electromagnetic spectrum while others vanish into the void? One culprit might be cosmic geography, mergers happening in the universe's worst neighborhoods. Picture a neutron star binary nestled deep inside a star-forming galaxy, where thick clouds of gas and dust swirl like fog. When the stars collide, their explosive light gets smothered before it can escape, like a firework detonating inside a wool blanket. This isn't just speculation. The few dark mergers we've pinpointed often trace back to galaxies brimming with young stars and nebulous environments notorious for their light-blocking debris. Even the most powerful telescopes might miss a kilonova if it's buried under 1,000 light-years of stellar soot. Then there's the question of distance. Some mergers might simply be too far away for their visible light to reach us intact. While gravitational waves travel unimpeded across billions of light-years, electromagnetic signals fade into the infrared, stretched and diluted by the universe's expansion. A merger at the edge of the observable universe could theoretically send detectable gravity ripples our way while its light dims to invisibility. But here's the catch. We've seen distant mergers with brilliant counterparts before, and nearby ones that mysteriously lack them. Distance alone can't explain the pattern. That's where exotic physics enters the scene. Some theorists propose that certain neutron star mergers might produce black holes so rapidly, within milliseconds, that they swallow the evidence before light can escape. In these scenarios, the entire electromagnetic spectacle, or jet's kilonova, all of it gets trapped behind an event horizon almost instantly, leaving gravity waves as the sole cosmic messenger. Others speculate about quark-nova models, where the collision triggers a phase transition in the neutron star material itself, converting it into strange quark matter. This process might release energy in unconventional ways, bypassing the usual light-producing channels entirely, but the most tantalizing possibility. We might be dealing with an entirely new class of compact objects, theoretical dark neutron stars. Hypothetical hybrids laced with dark matter or other exotic particles could collide without producing standard electromagnetic signatures. If even a fraction of mergers involved these shadowy imposters, it would rewrite our census of cosmic collisions and force us to reconsider what exactly lurks in the densest corners of the universe. Every missing counterpart is a cosmic test, one that pushes our detectors, models, and imaginations to their limits. As telescopes grow more sensitive and gravity wave networks expand, these dark mergers may finally step into the light. Until then, their silence remains one of astrophysics' most provocative puzzles, reminding us that the loudest crashes in the universe sometimes leave the faintest traces. Some neutron star mergers don't just defy expectations, they ghost us entirely. While most collisions announce themselves with blinding gamma-ray bursts and glowing kilonovae, a stubborn fraction emit nothing but gravitational waves vanishing from every telescope's gaze. These quiet mergers aren't just cosmic introverts, they're a direct challenge to our understanding of how these cataclysms unfold. If two ultra-dense stellar corpses slam together with enough force to warp spacetime itself, why doesn't the universe always bother with fireworks? The answer might rewrite not just merger physics, but what we think neutron stars are even made of. Take the gravitational wave event GW190421. When LIGO and Virgo detected its ripples in 2019, astronomers worldwide trained their instruments on the suspected patch of sky. Days passed. Weeks, nothing. No gamma rays, no ultraviolet afterglow, not even a wisp of radio static. This wasn't an isolated case. Roughly 1 in 5 neutron star mergers now appear to leave no electromagnetic trace whatsoever. The leading theory, these might be failed kilonovae, where the merging stars collapse into a black hole so rapidly that their debris never gets a chance to heat up and glow. Simulations suggest that if the combined mass tips over a critical threshold around 3 solar masses, the newborn black hole could form within milliseconds, swallowing the violent particle jets before they can escape. But there's a problem with this tidy explanation. Some quiet mergers involve neutron star pairs that shouldn't, by our current math, be heavy enough to collapse instantly. That's where exotic possibilities creep in. One radical idea posits that these silent events involve neutron stars made of strange quark matter, a hypothetical ultra-dense material where even neutrons break apart into their constituent quarks. If such stars exist, their mergers might release energy in fundamentally different ways, perhaps through dark channels like neutrino bursts or gravitational waves, bypassing light production entirely. It's like comparing a dynamite explosion to a silent electrical discharge. Same energy, radically different signatures. Then there's the environmental wild card. Imagine 2 neutron stars merging deep inside an active galactic nucleus, where a supermassive black hole's accretion disk churns with obscuring dust. Any electromagnetic signal would be smothered under layers of orbiting debris, leaving only gravity waves to escape. Alternatively, the stars might collide in near-perfect isolation, a cosmic void so empty there's barely any surrounding matter for the merger to interact with. No gas to shock heat means no kilonova, just the silent shudder of space-time. But the most intriguing possibility, these quiet events might represent an entirely new class of cosmic collision. Some theorists speculate they could involve exotic hybrids, like a neutron star slamming into a primordial black hole, an object so ancient and dense it predates stars themselves. Others wonder if certain neutron stars might be cloaked in strange-colored crusts, surfaces so dense they suppress electromagnetic outbursts during mergers. Every silent merger forces us to confront how much we still don't know, not just about how neutron stars die, but about what they truly are in their deepest cores. The implications ripple far beyond classification quibbles. If quiet mergers are fundamentally different beasts, they might contribute differently to the universe's heavy element inventory or skip element production altogether. They could also skew our estimates of how often neutron stars collide, since we've likely been undercounting events that leave no light trail. Most tantalizingly, they might be our best shot at detecting exotic states of matter that conventional telescopes could never spot. As next-generation gravitational wave detectors like the Einstein telescope come online, their enhanced sensitivity could finally tease apart these cosmic mimes from the noise. Until then, every silent merger remains a gravitational riddle, a reminder that the universe's loudest crashes sometimes speak in whispers. The debris field from a neutron star collision should read like a cosmic grocery, list predictable ratios of heavy elements like gold, platinum, and uranium forged in the merger's unimaginable pressures. Yet when spectroscopes analyze these stellar wreckages, they often find bizarre chemical fingerprints that make no sense. One kilonova might spit out 10 times more europium than our models predict, while another barely produces any platinum at all. It's as if these cosmic forgers occasionally forget the recipe, tossing random handfuls of elements into space without regard for the rules of nuclear physics. Take the merger GW170817 as the ultimate cosmic chemistry experiment. Its ejector contained staggering amounts of strontium, an element typically scarce in neutron-rich environments, while lighter elements like silver appeared suspiciously understocked. Even more puzzling, the ratios between rare Earth elements like neodymium and samarium deviated wildly from what rapid neutron capture or the R process should produce. These anomalies aren't just academic quirks, they're glaring red flags suggesting conditions during mergers might be far more extreme or far stranger than our simulations account for. The root of this chaos might lie in something physicists call fission cycling. Normally, the R process builds heavy elements by bombarding atomic nuclei with neutrons until they grow unstable and decay into stable isotopes. But under certain conditions, think temperatures exceeding 1 trillion degrees and densities rivaling atomic nuclei, these freshly minted heavy elements can fracture like overfilled water balloons, splitting into midweight fragments that then re-enter the neutron capture chain. This creates feedback loops where elements like gold get repeatedly destroyed and rebuilt, scrambling the final ratios. Some simulations now suggest fission cycling could explain why certain mergers overproduce elements like ruthenium and rhodium while leaving others mysteriously depleted. But there's a wilder possibility. Neutron star crusts might be contaminating the mix. Imagine two neutron stars colliding not as pristine spheres of pure neutron matter, but as cosmic onions with layered compositions. Their outer crusts only 1 kilometer thick but packed with heavy nuclei like iron and nickel from their pre-collapse days, could get shredded during the merger, injecting pre-made elements into the debris field. This contamination might explain oddities like the excess strontium in GW170817, since strontium forms more readily in lower density regions like crustal material than in the neutron soup of a merger's core. Then there's the dark horse of merger chemistry, magnetic fields. Their influence on element formation was long considered negligible, but recent models reveal they might steer nuclear reactions like invisible conductors. In mergers where magnetic fields amplify beyond 10 to the 16th Gauss, 1,000,000 times stronger than typical neutron stars, they could channel neutron flows into concentrated streams, creating localized nuclear hotspots where certain elements form preferentially. Picture a high-pressure hose blasting neutrons at specific atomic nuclei, forcing them to grow into lanthanides while starving others nearby. This might explain why some mergers produce erratic lanthanide abundances that resemble none of our controlled lab experiments. The most tantalizing anomalies, though, involve elements that shouldn't exist in merger debris at all. Multiple kilonovae have shown traces of light elements like carbon and oxygen, materials that require proton-rich environments, not the neutron-dominated hellscape of a collision. One theory suggests tidal forces during the merger might fling pristine material from the star's outer layers into space before it can be neutronized, preserving pockets of lighter atoms amidst the heavy element chaos. Others propose these light elements emerge from late-stage nuclear fallout, where highly unstable isotopes decay into unexpected byproducts long after the initial explosion. What makes these chemical mysteries so urgent is their link to the very origins of matter. If mergers can't consistently reproduce the element ratios we see in stars and planets, it implies gaps in our understanding of how the universe built its periodic table. Perhaps some heavy elements originate in supernova after all, or in processes we haven't even discovered yet. Every anomalous kilonova spectrum is a Rosetta Stone waiting to be decoded, holding clues not just about neutron stars, but about how every gold necklace, uranium deposit, and plutonium battery on Earth came to exist. Until we crack these elemental enigmas, the universe's grand chemical recipe remains half-written, with neutron-star mergers scribbling in the margins. From the missing gold to the ghostly silent mergers, from lopsided jets to hypermassive neutron stars that refuse to die, our journey through these 25 mysteries reveals just how much we still don't understand about the universe's most extreme collisions. Every time we think we've cracked the code, neutron stars throw another curveball, whether it's chemical abundances that defy prediction, gravitational wave echoes that shouldn't exist, or infrared glows that stubbornly outshine every model. These aren't just gaps in our knowledge, they're glaring signs that somewhere in the chaos of these cosmic smash-ups, physics is playing by rules we've yet to discover. The sheer range of these puzzles speaks volumes. On one hand, we have mergers that pump out enough energy to outshine galaxies, yet others vanish without a trace. Some forge heavy elements in abundance, while others leave the cosmos curiously starved of gold. Some birth pulsars that spin at the edge of disintegration, while others collapse into black holes so quickly they barely leave a whisper. And then there are the outliers, the mergers that flare up years later, the gamma-ray bursts that last too long or end too soon, the debris fields twisted into shapes no simulation can replicate. Each one is a reminder neutron stars don't follow tidy scripts. They're cosmic wildcards, revealing just how much we've underestimated the chaos of the universe's densest objects. But here's the thrilling part: we're on the brink of answers. Upcoming missions like the Einstein telescope, with its unprecedented gravitational wave sensitivity, or the Vera Rubin Observatory, set to scan the skies for elusive kilonovae, could finally decode these enigmas. Space telescopes like LISA will hunt for mergers in wavelengths we've barely explored, while advanced particle detectors might catch the neutrinos that have been slipping through our fingers. Every new instrument is a key, ready to unlock another layer of these cosmic riddles. So stay curious. The story of neutron star mergers is still being written, and the next chapter could rewrite textbooks. Whether it's a bizarre new state of matter lurking in their cores, a hidden law of physics governing their collisions, or an entirely new class of cosmic explosions waiting to be found, the universe has more surprises in store. Hit subscribe, follow the science, and keep looking up, because somewhere out there, two neutron stars are circling toward catastrophe, and when they collide, they might just shatter our understanding of reality all over again.